Down to the University of Texas. I don't know where he is now. He was at the University of Texas when I went to his seminar. That was some years ago, when I was young. Okay, let's go through an example. Now, somewhat similar to what you were doing in the homework, but with a slight complication. So we'll go back to that first lab we did, the flu lab, where we were looking at how the flu gets transmitted among our population here at BYU, Idaho. So you have a person coming in who's infected, and then they start passing that around. And we can take that, and we did, and punch that into Logger Pro, and we can do a deductive model where we just take the data, we find a function that fits the data, and then we use that function to either fill in gaps in our knowledge or to make predictions about things that we don't have data for, such as what's the maximum number of infected people, or at what point are we going to have 90% of the population infected, questions like that. So we can do it that way with an inductive or an empirical model. What you were looking at as you walked through the homework are deductive models. And so when we do a deductive model, we start not with the actual data, but by thinking about the problem. And we look at the problem, and we take what understanding we have of the problem, and we figure out what would be the general principles, the laws that should govern what happens in this situation. And then we formulate those laws into mathematical equations, and then we use those equations one way or another, in essence solve those equations, either in the highly technical sense that you have in algebra, where you take 3x is equal to 9 and you solve for x, or doing it numerically, where we just generate a set of data that come from our equations and then compare it to reality and tweak things until we get them to fit, or until they turn into BYU, Idaho. It's hard to believe that in my early youth, that BYU, Idaho, sitting there bouncing around, was actually a top-selling game. Pong. Sat there and just watched a little ball go back and forth across the screen. I even played Pong. We've come a long way. So if we take a look at the flu, we're interested in how the flu spreads. We just want to think about that in general terms. What are some general principles, some laws of biology that would help us understand how many people are going to become infected over time?
Well, there's a ceiling, right? I mean,
okay.
Only everyone can get the flu. You can't get like infinite people with the flu because there's not infinite people.
Right. So let's just put down some general principles that we can use to try and create a model. So we have that there is a maximum population. Or a ceiling that we can't get above.
Like that, there's a minimum population. So you can't have less than 0.
Okay. So yeah, so we have a minimum population. Which in this case is 0, the way you're stating it, although in some other situations our minimum population may not be a 0 population. Other general principles about how the flu is spread, just the biology of it and so forth. Lisa?
It doesn't always spread, so it's not a 100% transfer when you meet someone.
Okay. So, not every interaction causes infection. Good. Some other things, yeah.
Since a lot of times people are contagious before they show symptoms, it spreads really quickly because you don't know that the person that you're interacting with has the flu. So especially at the beginning, I mean, it spreads really quickly.
So initially, spreads quickly, and the idea here is that basically your infected person spreads it to the many uninfected individuals that are around. Good. Yes.
It'll probably be more like exponential than linear.
Okay. And let's dig a little deep. That's a great mathematical statement. What does it mean to be exponential versus linear? What characterizes exponential growth versus linear growth? Crystal?
Well, it increases greater over time. Like the first time interval or whatever, it may only spread, like you said, maybe those initially from the infected, but then they can go infect just as many, and it, yeah, see that. So that's my mathematical attend today.
Very good.
You're welcome.
Well, what we were trying to get away from is the mathematics. Mathematics makes wonderful sense to us, and that's great, and it's an important language to have. On the other hand, when you go out in the real world, for instance, I was at the International Congress on Industrial and Applied Mathematics in July, and they had a panel on careers in applied mathematics, and the big thing they talked about was the need for mathematicians to be able to talk to scientists and engineers, to be able to speak their language instead of speaking mathese. And so, we have that one. So if we look at exponential growth, the picture you're saying is, okay, we have the one person who spreads it to several other people, but then they spread to several other people, and then they spread it to several other people, and so forth and so on. It's a nice picture. Can someone characterize that in words?
Maybe this is kind of like a morbid way of thinking, and don't think I'm like this horrible person, but I mean, it's the difference between like a serial killer and a zombie, right? Because a serial killer, like, let's say they kill 3 people every week.
Okay.
Well, that means that there's a constant rate of 3 people every week that die.
Okay.
Well, let's say like a zombie, like, eats 3 people's brains every week and turns them into zombies. The first week you have 1 zombie, the next week you have 4 zombies, the next week after that you have whatever the next power.
It's a highly graphic example, yeah.
So there's actually like there's a video game where like so in Halo there's like a zombie mode where people like one person starts out being infected, and it takes a long time for them to start infecting like 1 or 2 people, but then it's just like rampant.
Right.
Oftentimes.
Good. I can guarantee that of the few things that you'll remember of this class in a few years, one will be the zombie example. So.
Well, I mean, an engineer would understand that, right? So.
Why don't we pause that and start it up again? Because it only does the 15 minutes.
Yeah, I could just. Oh, we're at 8:30, so we're good.
Oh, okay, great. So now, if we go back to what you talked about with linear, you used an important term. You said that there was a constant rate, and in describing exponential, you talked about an increasing rate. So in very general terms, we run into that. Exponential, if you really look at either exponential growth or exponential decay, what you're really looking at is percentage basis change. So you change by a certain percentage every time, either increase by a certain percentage or decrease by a certain percentage. Whereas down here, you it's not a percentage basis, it's just a set rate of change, constant rate. You change by 3 every time, you change by 2 every time. So that's the difference between linear and exponential growth, whether you're going up on a percentage basis or just at a constant amount every time.
Keep saying stuff. Like the more people are infected, the lower the rate is. Because after a certain point, like you can't give the flu to somebody who already has the flu.
So here we know that after some time, the rate decreases. Reason being, there are only a few uninfected individuals. If there are only 4 people to pass it to, you can't have 20 people get the flu. And so the number of people getting the flu during a certain period of time will decrease because there's just fewer people to get the flu. Good. Anything else that you can think of that would describe how the flu spreads?
Do you take into account people who are immune to it?
That would be good. So there is a question of natural immunity. Well, not necessarily natural. Just plain immunity. People who got the flu shot, people who are naturally immune to it. Apparently I was naturally immune to H1N1. So my whole family got it, but I did not. So, why? Who knows? Maybe I got one as a kid. The other concerns or things that we might need to want to take into account.
Usually it's spread by being in the physical presence of someone else.
Okay. So, if we want to get down into the actual mechanisms, it's spread by some form of physical contact. Now, that might be the fact that you physically contacted the door handle, and 2 hours later I physically contacted the door handle, and so I now have your virus on my hands. But that's in there, yes?
Also, after we know the flu's out, people take precautions. And so that would affect it.
Go along with immunity, that you might also have, in addition to those that are immune, some people's health status may either be impaired due to other medical conditions or something, or other conditions, or their health status may be even more improved due to whether they're more physically active, which means their immune system is going to be a lot stronger or something like that.
Good. So the effect of people's health. Susceptibility to it, yes.
I'm gonna restart it.